Hello, my name is Uwe Hartmann. I'm CTO of Image Engineering. IEEE-P2020 is the standard for image quality in automotive systems. It's the first international standard in this topic. So how can it help you? Let's have a look at that. So the standard is finally there. It has been released by IEEE. It is available for download from the website. I personally, with colleagues, we started contributing to this in 2016. So it took quite some time to develop this standard. So many experts contributed their knowledge into the standard, and it's the first standard in this area. So the standard consists of 7 main image quality factors. That doesn't mean that these are all that you should care about, but these are what the work group decided are very important ones, and these are the ones where we saw that it needs to be addressed in standards. So that's why these have been defined. So they are essential, and I think it is important to test some or all of them depending on your project needs. So let's jump into each of these image quality factors that the standard provides. But first, some word about testing in general. So if you improve your testing, you can actually improve the device performance. So what do I mean by that? So what happens a lot, I have seen in my business work, is that a lot of people and engineers see the testing of the camera as an annoyance, that is an extra step that the customer asks for. And this is only needed for the final validation, and then they drive around with cameras in the car and then hope that nothing happens. So when you start to design a camera or think about how should it look like, then you start the sourcing. So what sensor, what lens do you have? Then you start to develop to bring everything together. You configure it and try to find the best settings for just getting an image. And then you start into tuning, and then at the end you validate. And it seems that people care only at the end at validation. So then they go out on the street and drive around. So that can be something like this. So you take your car, the camera in the car, and then you drive, and then you try to find certain areas where things can happen. Like here, you go in a tunnel, you have a challenging situation with some shadow persons, you go from the dark into the bright. So these are specific scenes. Or here you look nearly into the sun, and you see obviously with this camera there is some highlight issues. So that is what you then see on the road, or here in nighttime. So the typical city night, that's a problem because you have bright lights and in general dark environment. That causes trouble. Or here where you need to look very far, basically headlamps. It's a problem to configure your sensor and your imaging system correctly for that. Or in this example, you have flicker. So these so here in this example, so these lights, they flicker. So they cause also this flickering effect in the camera that is at least an annoyance, if not even a detection problem. Okay. So what many people or many projects that I've seen do is they only add validation when they want to give the camera to the final customer. They investigate these and they see these issues that we just have seen, and then they have to potentially go all the way back, maybe even to sourcing, and realize, oh shit, we took the wrong sensor. So that's maybe not the right or the best way to do. So with incomplete and weak testing in the lab, the whole process will be delayed, and any finding in validation, and that leads to a risky timeline and not ideal performance. So what do I mean by testing? This, what you see here, is what many people see as testing. So they take an image with a color checker or a very simple resolution chart, just some edges, and then they say, okay, that's testing. No, this is not what you need for modern cameras. Modern cameras in automotive are very complex. They have huge dynamic range. They merge multiple images from either from multi-exposures or from split pixel designs. They have to work over a huge range of temperature and so on. So that is, these kind of tests is maybe to see if it's functional, but that's not really a proper image quality testing. So what I think and what I see in many projects, what's really important that in the early time you already start to do proper testing. So the earlier the better. So if you do the sourcing, you have to decide what sensor to use already then, perform a proper test and not just according to data sheet, get it into testing so that you can see if it works for your workflow, for your needs. And only with proper testing, then you can see directly what works, what does not work, and that gets you out of these nightmares that at the very end in validation phase something comes up and then the decision is, okay, either we ruin the timeline completely or we ship a bad product. And that's not a decision you want to make. Okay, so that's why proper testing is important, and that's also why we have like IEEE-P2020 as a standard that you can improve on this side. So let's have a look at the different aspects of image quality factors that are defined in IEEE-P2020. So one category is the contrast performance indicators. That is something that is actually new. That has not been, there is no counterpart in existing standards, or that it's just a modification to existing things. So contrast performance indicators is something new, and it has shown in our daily experience here in our lab, but also with many, many customers that we work with, it has shown that it has a huge potential to be really a big help for the development process. Not only for benchmarking, but also actually to work with the camera. So what does it do? So one of the contrast performance indicators is the CTA, contrast transfer accuracy. So you can see it like that. You have in an object, you would have two areas that form a certain contrast. And you want to answer, is my system under test capable to reproduce this contrast? Because if it fails for any reason, then that might be a problem. Because a lot of detection, or all detection algorithms for ADAS systems, they need to see some form of contrast, of object contrast. If the object doesn't form any contrast anymore, you cannot detect it. So what you see, so in real life, you have two objects. You have an object in the background, and then that can be simulated with a test target where you have these patches. That forms two distributions. So the distribution dark and the distribution bright. That is just like a histogram for these two distributions. And now you go pixel-wise, and from distribution A, or distribution dark, and distribution bright, you take one pixel there, and then you calculate the contrast between these. And then you do that repeatedly, over and over again. And that gives you a probability density function. Within this probability density function, you define bounds, and everything that is inside the bounds is good, that is actually reproduced. What is outside, that is rejected. So then we can create a single value that tells you what is the ratio of, in the probability density function, that values are inside my bounds and that are outside. So 100% means everything is inside the bounds. 50% would mean 50% is in, 50% is out. So the higher, the better. What is now the interesting thing, when we measure that, we cannot only measure for one contrast, we measure for many different contrasts. And that is something that we can provide. So then as a result, what you get from this measurement is a map. On the x-axis of this map, you have the average luminance. That's the average of these two patches. And then on the y-axis, you have the contrast that it forms. And then in color encoded, that is the contrast transfer accuracy, where we just said 1 is perfect. The lower the probability that you can actually distinguish these. So with this map, you can describe a lot of effects in the camera. So first of all, you have different positions. So you can have, that is like on the left of the image, you see there is the headlamps of a car and then a darker car in front of it. So that is a very bright, high contrast scene. So that's somewhere in the top or top right of my map. But then you have also some rubber pieces or tire pieces that is also in the lower left of the image. So that is something, a dark object on the dark road, So that is low light, low contrast, that's in the lower left. That's the very challenging part of imaging. So this way you can see where are the different areas that I should have a look at. But I also have some examples here where to look at. So here's the example where we have a road. Only the headlamps are active, but because I'm driving relatively fast, my camera system should look beyond the headlamps. So that means what I need to see is really low light, the low light performance of my camera. So for that, I have a look at the left region of my map. So what you see here is more like bluish purple. So that means, okay, I have a significantly reduced contrast transfer accuracy in this area. But that's where you have a look if you want to compare systems. How is my low light performance? Another aspect that you can have a look is a low contrast performance. So here, as the example, you enter the tunnel. It's not very dark. I mean, it's daylight, but these persons on the left, there's actually 3 persons. But because of the clothing and then something dark in front of a dark background, it's quite hard to see. So this is low contrast performance. And that is also very interesting to see from a camera. And that is more the lower area of the map. You see that I marked that here. So that is going from low light, low contrast to bright light, low contrast. And that's where you can see where you might lose some information. So that's where you want to look, can I really distinguish these low contrast objects? But then we also have an effect, especially when we have like HDR modes in a camera. So you see the car, the silver car is approaching my car that I'm driving from the sunny outside into the tunnel. And when I see these 3 images, when it's completely in the tunnel, I can see the car quite well. And if it's outside, I can see as well. But in the transition zone, it happens that it gets very noisy and I lose the contrast. So this is what is also sometimes called like SNR drop. So this is a transition zone between different exposures or different gain settings to create an HDR. And that's where you have a look at a certain contrast and then all the way above along the different luminance. So then if you have some peaks in there, that's exactly what how this effect can be described with the measurement. So that's extremely powerful to find out about the tuning of these configurations, because you have many different settings that you have to make to create this HDR, and that's easy to make a mistake there. So with these tools, you can very nicely see if it worked well or not. Another typical issue is the highlight performance. So you saw that in the previous video here, just a frame. One camera in the top has a highlight issue, so the clouds getting purple. While the car, the lower image is much better, so you have nearly the sun in the field of view, but there's no color shift and it can reproduce the clouds. So it's the same situation, it's the same brightness outside. And that's something that you can nicely see here on the right side. So that's the highlight performance. So you see, such map can give you a lot of different information for different things. So it's one measurement that tells you a lot of different things about your image. So how do we measure that? So the standard defines 2 different recording methods. So one that is called spatial recording. So we use for that the VLS, the versatile light system. So with that system, you can create 6 light sources that have a certain target. Each target has 36 patches. So that means that you have 218 luminances in the scene. And that means spatial, so different luminances are recorded on spatial different positions. That is, the spatial recording, so with 6 light sources. The contrast for that is the temporal recording, which, for example, you can also do over temperature. So for the temporal recording, you take a light source that you can control quite well, that gives you the luminance. So we use a Vega light source. So with that, you can control the intensity, the light luminance very well with this over a huge range. and then you put your camera in front of that, and then you take one image after another. So change intensity, take a picture, change intensity, take a picture. So this is then temporal or in the time domain, the recording. Here, the nice thing is this is also something that you can easily bring into a climate chamber. So if you take our IQ climate chamber, you put the Vega outside of the window, the camera inside, and then you can perform all the measurements that we've just seen over temperature. So, for example, so what is the differences and pros and cons? So for the temporal recording, like on the left, you can measure CTA, CSNR, CNR, so different measurements from the standard with a small and easy setup. It's easy to integrate into your lab, or into you could even do it on a bench or on a desk. The influence of flare from a lens is minimal. So you can perform this for, or even with a cheap lens, it's no problem. But it requires a high level of control over the camera. So this works if you can, you need to be able to set the exposure and freeze the exposure. So no auto exposure, no auto gain control, auto white balance, or local tone mapping. That is not allowed if you do the temporal recording. And for flicker, you can just do a quick check, because to do a complete flicker test with this setup would mean, take far, far longer. So for that, there is the spatial recording setup. So the VLS with multiple light sources and then with test targets on top of that. So also with that, you measure CTA, CSNR, CNR with a very flexible setup. Additionally, you can also easily measure the MMP, a flicker measurement we're going to talk about later. With that setup, you can test all sort of images, including processed images. But you need to align well to mitigate flare. So that's why we made it so flexible. So if you might need to align the light sources to your camera. So that's a big benefit, that it's so flexible, so that you can do that, but that has an impact on that. So here's an example of a temporal CTA over temperature. I just talked about that, so that's definitely a possibility to park that. And you see here a sensor where we get into a huge, or where we get different behavior, of course, over temperature. So this is it's not optimized off-the-shelf camera with automotive grade sensor. So we just took the off-the-shelf camera. This is not the best that this sensor can do, but we quite nicely see this is something that you could get from as the initial configuration from your sensor supplier. So there is some behavior. So we measure here the CTA for channel 1 to 4. In this case, it's an RGB camera with over the range of 50 degrees Celsius to 120 degrees Celsius. And what we see over temperature, so we have a reduced low light performance. So the more we heat up the camera, we reduce the low light performance. We get noise or contrast loss between the HDR exposures. That gets quite significant the higher the temperature. And we have a buck-in readout. So there is a misconfiguration on the sensor. We know what it is, but it's quite interesting to see here. So if there is a bug in the readout, something that is easily to miss when you just go outside on the road, here in the data it shows up very easily, and so that you know, hey, there is something wrong with my measurement. So now have a look at another image quality factor. So one is the dynamic range. So typically, dynamic range is defined as a ratio of the maximum luminance and the minimum luminance that a system under test can reproduce. So the maximum is then defined by saturation, and the minimum is defined by the signal-to-noise ratio. Typically, you say when the signal-to-noise ratio equals 1, you have a loss of information, and that's the lower limit, minimum luminance. The problem is, if you have, for example, flare or other effects that reduce the contrast, which you can easily have in HDR images, the SNR will actually get better. And therefore, also your measured dynamic range gets better. And that can lead to misleading results. So that means that the traditional way to measure dynamic range has its challenges, to say the least, for automotive grade cameras. Therefore, IEEE-P2020 addressed that, and there's a definition of CNR, the contrast to noise ratio. So the idea is that we not use the mean value divided for SNR, the mean value divided by standard deviation. We take the contrast between two patches. And now you see, two patches. That's something that sounds familiar as we had with CTA measurement. And yes, that is something that you can do as well. So in the document of the P2020 and in the development, there is a test target that is limited to a default contrast of 2:1. And during the development of the standard, it turned out that the used targets were varying a lot, which caused issues in reliability and repeatability of the results. So there were single patches that did not have the contrast that it was supposed to be, or that there were some color issues in there. So that's why we checked how can we do it differently. And with the in the data that we get for CTA and CSNR measurement, what I just talked about as contrast performance indicators, we can also calculate the CNR. And with that, you have you can get the CNR not only for the 2:1 contrast, but also for any contrast. And that is a big benefit, so that you can calculate your dynamic range flexibly for different contrast, but it is compliant with the standard. So that looks like this. You have, again, a map. On the x-axis, you have the average luminance. On the y-axis, you have the contrast. And then in color, you have your CNR. And now, according to the standards, it's 2:1 is that shall be used, but others are definitely a possibility. So now you just have a look at a third Michelson contrast, so 0.33. That is where you need to have a look if you want to know about, according to the standard, what's the dynamic range. But now with this approach, you can also check at other contrast. And that is definitely a benefit, because if you have a task like a road sign detection, it's higher contrast task than you want to do a pedestrian detection, where you need to check like a person with dark clothes in night time and so on. So that's a different test. Something to talk about dynamic range. So today's sensors, high dynamic range sensors, they need a very bright light source to check the limits, especially when you want to bring them to saturation. So sensors are typically configured that way that it's okay to have the sun on the horizon in the image. That might bring it to saturation, but only that. So that means if you want to simulate this in the lab, you need a very bright light source. And that's why we introduced Arcturus. Arcturus is a light source that works well together with the Vega light sources that you've just seen in previously. And that is what what is so bright that you can actually bring automotive grade sensors into saturation. So we are about 1 megacandela per meter square, while still being very stable and consistent. So you can go over a huge range of dynamic range, change the intensity of that light source, and perform tests with a high stability. So the device itself will control itself and will be very stable. It's flicker-free, and you can use that also with very, very short exposure times. If you need flicker for checking, feel free. There is flicker simulation if needed, so you can put a flicker signal onto that, but per default, it's flicker-free, DC-driven, so you can do a lot of tests on that. So especially you can combine that with the Vega and the Arcturus, and with that you can scan through a huge dynamic range for imagers and really get into the details throughout the entire range of imaging with your camera. So we already, let's have a look at flicker. So when we say flicker, these are the effects that I typically talk about. So for example, you see there on the left, there's a road sign, these 80 kilometers per hour. For a couple of frames, it's invisible to the camera because the camera has a problem with the PWM that this road sign has. Also, in the scene that you see in the top right, that is something of an annoyance because these road lights, they also use PWM, so that causes a general flickering effect on the entire image that you capture. And that's at least an annoyance, if not really a disturbance for the detection algorithm. You see these videos in the lower part where you have these different artifacts. That is actually the Vega light source creating different kind of frequency or duty cycles and phase, and that can cause then quite different artifacts in the image. So with these light sources you can create these and really check if like flicker mitigation in the sensor does actually work. In P2020 there you see the metric of MMP for that. MMP is based on the observation of a certain area in the image. So let's assume, or let's observe a single pixel over time. And if you have some flicker in the image, it will change the intensity to a high and to a low value. Or if you have some bands going through the scene because of flickering artifacts, that will also cause that this pixel will get brighter and darker over time. So that gives us, if we have this flicker, that gives us two distributions in the over time, which we can then observe. So now we can use the same approach as we use for CTA. We calculate the probability that a certain value falls inside this distribution or that it's outside. So you see that down there. If the flicker mitigation is on, all values are just with some temporal noise, but they stay very much at the same level, so that all falls into a certain bounds. So that means there is no flicker in the image. As soon as we have flicker, so the flicker mitigation is turned off, we will get two distributions. So that means that a lot of these values fall outside of the mean value, so of the area that I would expect. So I get a low MMP. How does that look like? Again, we create a map. So yellow means low flicker, blue is high flicker in the scene. So now on the x-axis, we state again the luminance at which this was measured. And then on the y-axis is the frequency at which it was tested. For the test itself, the test now here is then defined for one specific duty cycle. So here for 10% duty cycle. And what is important for the capture process, we also change the phase. So you can imagine you have a camera that is capturing constantly an image, and you have a flickering light source. Depending how they work to each other in terms of timing, they can create flicker or no flicker, so it depends on the phase how they are time-wise next to each other. So that's why we need to scan through the entire phase, and that's what we can do with the Vega light source with the VLS setup. So to get into these maps. So now here is an example. So get that on the left is the MMP for 10% duty cycle, on the right is the for 90% duty cycle. So what is interesting to see here then on the left, so that's for the different color channels of the sensor. So what you can see is that the flicker depends on the intensity. So depending on the intensity, you have flicker or you do not have certain flicker artifacts. And that's quite obvious, but that's not what all tests do. So many tests for flicker do not change the intensity. So here this is done, and this is very important because you see, depending where you are in the region, you have flicker depending on the intensity. But also for the frequency, it's quite interesting. So you see here, for example, at 100 Hertz, flicker is perfectly mitigated, at 200 as well. But in between, you already, again, have strong flicker. So that if your sensor has flicker mitigation, it is obvious that this flicker mitigation works well for a certain frequency, but not for all frequencies. And that's very important to check and to see. So let's have a look at noise, also an image quality factor that is important. Here, it's not that the P2020 provides something fundamental new, but it's well defined now, and that's something that you can reference. So it extends the established methods for and defines operation conditions for the automotive camera. So other standards that are out there are typically then used for machine vision or for like photography, but they do not always apply then to automotive environments. So what the standard defines are many different metrics for the dark noise. So as the dark statistics are quite important for designing and for checking your sensor, so there's different metrics that are then defined for that. What is interesting is that this is important to perform, especially dark signal measurements are important to perform over different temperatures. So that's where, for example, our IQ climate chamber is of interest, because it's it's a setup where you can easily change the intensities or the temperatures and then measure the performance of the imager over temperature. Another measurement for noise is then the SNR. As I said, SNR itself is a well-established metric, but how exactly it shall be measured and some of the definitions are not well defined and not established for the automotive environment. So that's why it has been done here. So what you see there is an image of an example setup in the top right. That is actually the LG3 with our TE269 test target. So with this setup, you can perform the noise measurement according to IEEE-P2020. So you get the SNR plot and you get a photon transfer curve from that that you can then use also to define like SNR drops and to really characterize the image. The next image quality factor that is defined in the document is flare. So flare is in principle light that hits the sensor but does not originate from the corresponding position in object space. That sounds complex, but what it means is like you have stray light or you have some light from the side from the sun, and that causes a signal even though the sun is not even in your field of view. So you have your car, you have a camera on behind the windshield, and then the sun from high above shines onto your camera, and that causes a signal, even though the sun is not in your field of view. And that's what we call flare, or that's what we would like to characterize. So there's a different approach how you can do that. So in the standard, there's one that is more closer to the ISO standard, where you have a bright white area and then black dots on top of that. But I think the most or the more interesting measurement that is defined here in P2020 is the flare measurement, where you have where you scan through the entire hemisphere and then change your camera. So you can do that by either changing the position of the light source or by rotating the camera. But what you need is a bright light source with collimated light and from different angles. So you see in the upper left an example of a measurement we did in our lab of a camera where we used a very bright light source, which is actually required to do so, that you need a proper bright light source, because if you want to check the flare behavior for a car, the typical flare light source that you have in the car is the sun. So you need a very bright light source. And as you see in the lower left, it's defined, you need collimated light. So you need to project one bright dot from, with collimated light. And in the upper right, you see that the collimated light beam that we create with our flare light source, we actually had to make some dust and in the room so that you can actually see that. So you see over the entire length of the lab, several meters, it's exactly the same shape. So that's a very nicely collimated light that can then be used for the measurement. So that gives you also a map, but the map is then about the different angles. So you rotate the camera for the entire hemisphere, and that will give you then information at which angle you got more flare and at which you got less flare. So from that you have the chance to investigate further what might have caused the flare in your camera. Spatial frequency response is another metric in there. Also there it is nothing really complete new, so like with noise, but it's good to define that in the automotive environment. So the method that is also used here for the SFR or spatial frequency response is what is called ESFR in ISO 12233. So that's the slanted edge approach, as it's commonly called. So when the workgroup started, there was the ISO standard 12233. 2017 was just published, and there was no indication that there's going to be an update anytime soon. So P2020 started to define modifications to the standard that are actually needed. While it took a while to develop P2020, and the ISO committee continued to work on ISO 12233, it is a case now that that ISO 12233 was published before the IEEE P2020. So that's why the P2020 references the ISO standard and does not describe certain modifications to that anymore, even though it was already identified by the experts in the IEEE committee that these findings and that these modifications are useful, especially for the automotive application. Therefore, it did not describe the same thing in the standard than what the ISO does, so it just references that. What is done in the P2020 document is to define certain metrics that are derived from the SFR. So the SFR, you see that in the lower left image, the red line, that's what you might measure from a camera. That is what you get from a single edge, and that is what you measure, and from that you can derive different metrics. For example, SFR 10 or SFR 50, so that is the spatial frequency for a given response. But also like SFR at half Nyquist or at quarter Nyquist, that is the response for a given spatial frequency, so in the opposite direction. For human vision applications, which you also have in automotive, for like rear view cameras or in-cabin application, you then have the acutance, which is the weighted SFR with the contrast sensitivity function for human perception. And then there are some definitions how you get the corner variation, SFR 50 and acutance, so that with that you can identify misalignment of sensor to lens to sensor, and the SFR max as an indicator for sharpening. So if you have a processed image, this SFR max is an interesting metric to have a look at. How much sharpening do I have in the image? And it needs to be reported as a set. So because with much sharpening or a lot of sharpening, you can easily increase your SFR 50 value. So if you just know the SFR 50, you don't know if you still have a good image, because it might be just a result from sharpening. So the combination of SFR 50 and SFR max, with that you get really the information that you need from your camera. Okay, so the geometric calibration validation. So that's not that much about benchmarking a camera, but it gives you a framework to see how, and it's standardized test to evaluate how good a geometric calibration model works. It does not tell you how to create the geometric calibration model. And it doesn't prefer any model over another. It just provides you with a tool set to say, is the geometric calibration model that I get from my camera, is that any good? Does that actually work for my camera? And that is what the geometric calibration validation part of the IEEE P2020 does. Next to it, it's also very useful as it defines many metrics that are loosely used out there. So you read them a lot, but it might be that they are not defined always to the same extent, or that they might have a slight different meaning depending who you ask. So with these numbers or with these metrics defined in the standard, we hope that we can help the industry to communicate better with partners. So what's next? So the workgroup continues to work on the standard, even though it's published now. And this will lead to further improvements and enhancements of the existing methods, and new measures can be added. So in the document, you will find a lot of sections that are informative, especially like in noise and in dynamic range. There are still things that have been identified that we would like to do in the future, but that are not done yet. So that have not been validated to the extent that we would love to. So therefore, we will continue working on that. But also new topics have been addressed and are discussed right now. For example, color. So to answer, can the camera distinguish a red from a yellow? Or how well can it do that? Or dynamic behavior. So how fast does it react to a changing light if you enter a tunnel or exit a parking lot? And motion, so what is the impact if the camera object is moving, which is the case in cars. So it's hardly the case that the camera is used when the camera itself is stationary. So if you are interested in participating in this work, or if you say, you think there is something particularly that the workgroup should address in a future release, now is the right time to join the workgroup. So get in touch if you're interested, reach out to me. I'm happy to introduce you to all the right people and get you into the workgroup. So thanks a lot for watching. And I hope this video helped you to understand IEEE P2020. If there's any question, please reach out to me or to our friends from our office in China to get you all the information that you need. Thank you.